This is going to be true all the time. You got to be a little bit careful when you're making generalities here, though. When you're going from a higher to a lower index, because something strange can happen. Here's a question. Let's see if we can try this out. A beam of light in water makes an angle of 65 degrees to the normal. So again, we have light coming out of the pool and going up into the air. So you have like a flash or a flashlight or a light down at the bottom of a pool. Beam of light in water makes an angle of 65 degrees to the normal. When the beam emerges into air, what angle does it make with the normal? Okay, none of the above, because what happened? What did you get with your calculator? Error message, right? What happens? You have a sine of an angle that's bigger than 1, right? We've got a problem. We say n1 sine theta 1 is n2 sine theta 2. And so you have theta 2 being equal to the inverse sine of n1 over n2 sine theta 1. And so that's the inverse sine of 1.33 divided by air, which is 1.0029. So it's essentially 1.33. It's approximately 1.33 times the sine of 65. And that number inside the parentheses turns out to be 1.205. You can't take the sine of an angle, the inverse sine of a number bigger than 1. So we go, what's going on here? Well, it turns out that this angle is bigger than what's called the critical angle. At some point, we reach a point where refraction, let's look at it this way. If I'm going from a lower to a higher index, again, that light ray gets bent away from the normal. But I could imagine increasing this angle until the light ray is somehow bent at 90 degrees from the normal. So here is, say, the water, and here's the air. And here is some theta 1, which is going to be, I'm going to call the critical angle. And theta 2, we're going to say, is 90 degrees. So you can calculate that critical angle. We know we have n1 equal to 1.33 and n2 approximately equal to 1. It's 1.0029, but let's just say it's 1. Use Snell's law and see if you can find what theta 1 is equal to. That's right. So at a certain, beyond this angle, we basically reached the maximum amount of refraction, right? Anything beyond this is going to produce a sine of an angle, or a sine, inverse sine in here greater than 1, right? And so you just can't see that. That light's just not going to escape. And that's called total internal reflection. Okay? So anything beyond this, there is no refraction, and what we're going to see is just pure reflection inside the material. So this is called total internal reflection. Anybody get the angle? What is it? 48 point what? 48.9? So about 49 degrees, okay? So what this is saying is that for at least for the water-air interface, it may be different depending on the materials, but for the water-air interface, if you have a light going from the water to the air, and it's at an angle bigger than this 49 degrees, in the previous problem the angle was 65, so it was definitely bigger than 49 degrees, you're going to have what's called total internal reflection. No light is actually going to escape, and it'll just be purely reflected inside the material. So let's see if we can try it. Here is a tank of water. And make sure everybody can see this here. Let me see if I can move it without spilling it. So I have here just a lamp that I can change the angle with, and here is the along the 90-degree line, or along this line here, we have just a surface of water with air, and I'm going to turn the light on. And so when it's with when it's at a 0 angle with the normal, the light just goes straight up, right? And as I increase the angle, we see the angle increasing with the normal in the air as well, until I reach somewhere around 45, 46, 47, 50 degrees. And right around 50 degrees, you can see, can everybody see that? You can see total internal reflection, right? There's no light actually escaping. Now, there's some combination of the two when you're kind of at that critical point until you go past that critical angle and it completely turns into total internal reflection, okay? So the key point here is that when you're going from lower to higher index, the light ray's always bent toward the normal. When you're going from higher to lower index, the light's bent away from the normal, but you got to be careful and worry about that critical angle. If you're beyond that critical angle, you're going to have total internal reflection. Okay? We will deal more with this on Wednesday.